two chapters that we have studied. Mostly it will be on the first chapter, critical Mach number, wave drag, and we use the formulae to get some numbers. Let's first start with estimation of critical Mach number. So this is a real life example. So we take NACA 0012 aerofoil at 0 angle of attack, and the CP distribution is as shown. Notice that the minimum CP value is minus 0.43, which is, now this information or this particular result was obtained using wind tunnel test at a low Reynolds number. 3.65 million is a quite low Reynolds number. So this is a low speed CP minimum value, so called CP0 is minus 0.43. Our job is to estimate the critical Mach number for this aerofoil accurate up to 3 decimal places. So how would you do that? Yes.
Sir, my name is Vishnu. We will try to plot the CP with the Mach number and wherever it will intersect with the universal line, so that we will consider, or analytically also we can say.
That's right. So there are these two equations. The one that says that Cp minimum is equal to Cp0 minimum divided by root of 1 minus m infinity square. On the right hand side we have the formula for Cp critical. So just solve it. So that's your task now. Okay. Take out your calculators, take out your notebook. I am giving you a hint. Start with m equal to 0.7, because Mach number below 0.7 normally you don't expect to have a critical Mach number. Okay. So please start. So what you do is take m equal to 0.7, put it in the left equation, get the value of Cp min, put the same Mach number in the right equation, get the value of Cp_Cr. If they don't match, then you change the value of Mach number, and like that there will be a Mach number at which both these equations will give the same value. So the first person who solves it should raise the hand. And we want it accurate up to 3 decimal places, which means you will have to go first 0.7, then maybe 0.71, 0.72, 0.73, 0.74, and very soon you will come to know at what Mach number both these equations give the identical solutions. If you have a calculator that is programmable, then you can set a small program. That will be easy. Just put Cp0 minimum divided by root of 1 minus m square is equal to the RHS and solve for m infinity. Yes.
Sir, the answer coming is 0.737.
Right, that's the correct answer. M equal to 0.737 is the right answer. Okay, in the interest of time, I think I ask you to leave it, do it yourself offline. You can see the solution that we got. So we began with 0.7, LHS, RHS, and then we kept on increasing. At m equal to 0.737, LHS and RHS are matching with the 3 decimal places. Okay. So with this, I think one question in the quiz you can already solve. The giveaway. Yes.
So what did we take the value of gamma?
What do you think?
1.4.
Why 1.4? What are we dealing with? Which fluid are we dealing with?
Air.
At Mach number 0.7 or so, what is the value of gamma? 1.4. That's it. So it dissociates at Mach numbers which are very high. So then you will take a lower value. So you are actually trying to now solve the quiz question. Okay, any more doubts? Straightforward. It's just a matter of matching left and right. Okay. Next question is slightly more difficult. Now our job is to estimate the wave drag of an actual aircraft. Okay. So I have chosen this aircraft, Lockheed F-104 supersonic fighter aircraft. I will talk about this aircraft slightly as you solve your tutorial. First of all, by the look of the aircraft, what can you say? What are the features that you see? As far as wave drag is concerned, what kind of features do you see? Can you call this as a swept back aircraft? Yes or no? No, the answer is no. How do you measure sweep? Not just the leading edge, not the trailing edge, but at the quarter chord. Okay? So the quarter chord sweep is not there. So this is the straight wing with taper. It has taper, but it doesn't have sweep. So now we have spent so much time looking at sweep, variable sweep, forward sweep, but this is a supersonic aircraft and there is no sweep. So in a supersonic aircraft, how do you allow aircraft to fly without providing sweep back? What needs to be done?
The thin
Wings, thin wings, that's right. Do you remember which is the first aircraft to fly supersonic?
Bell X1.
Bell X1. Did it have sweep back?
No.
No. It had very sharp leading edge and thin wings. So that's the right answer. If you want to fly at a high speed and still don't want to give sweep back, one of the many options available is thin wing. So that means this aircraft is a thin wing aircraft. Can you see in the front view? It's very clear. It's a very thin wing aircraft, isn't it? T by C is very small. Do you agree? Yes or no? Okay. So this aircraft weighs 7260 kilograms and it is flying level at Mach 2.2 at 11 km under IFC conditions. If the wing area is 19.5 square meters and this is the reference wing area, which means the area of the wing as seen in the top view, including the part inside the fuselage. But nothing to worry, that is the reference area and that is what is used in the calculations for lift and drag. Okay. So when we say L is equal to half rho V square S CL, that S is the wing reference area, which is given to you 19.5 square meters. Mach number is known, altitude is known, weight is known, and there are these two formulae for a thin aerofoil or for a thin wing. Now we are going from aerofoil to wing. Actually speaking, there is a slight variation, but for this purpose we are going to just neglect it. Okay. So we assume that these formulae are applicable also for thin wings. So CL is 4 alpha by root of m square minus 1 and CD wave is 4 alpha square divided by m infinity square minus 1, because wave drag is going to be predominant only when you have Mach number more than 1. So using this information, please solve. Get me the value of wave drag. If you have any queries or questions, you can ask me. First of all, I want to know the procedure. How will you solve this question? What do you need to estimate the wave drag? Yes? So tell me, how do you get wave drag? Because you said you know lift.
Yes.
Yeah. So lift is equal to weight in level flight. Yes. So because W is known, lift is known. Okay, then?
So lift is known. After that, we need alpha from CL. So we know CL is lift divided by the dynamic pressure.
Into area.
Into area.
Correct.
Yeah. So dynamic pressure can be estimated using the velocity of the aircraft.
Right.
So velocity of the aircraft can be estimated from the like Mach number into the velocity of sound.
Right, at that altitude.
At that altitude.
How do you get velocity at that altitude?
Velocity at that altitude, though, we know the velocity of sound is root of gamma p by rho.
Okay.
So pressure at that altitude.
You have to calculate the pressure of the altitude. Okay.
So
how do you calculate that?
That I don't know.
Okay. So let's go to somebody else now. Vardil, please take a mic. So let us start from the place where he says velocity of sound has to be estimated at 11 kilometers.
Velocity of sound can be estimated by the equation velocity of sound is equals to under root gamma RT
gamma
And-
RT, okay.
And for the T relation, we know that from 0 to 11 kilometer in the standard atmosphere, the decrease in the temperature is minus 6.5 into 10.
Yeah, decrease is not minus 6.5,
Slope.
decrease is 6.5,
sorry.
that will become increase. Okay, got it. 6.5 degree per kilometer altitude, there is a drop in temperature. From what value?
From sea level.
How much is that?
Sea level is 298 Kelvin.
No, you have already made it 10 degree hot. Okay, so now I'll take you step by step in the solution. Now what I have done is there is a color coding here. So there are some red lines which means questions, and there are some blue blue ones are the answers. Straightforward. What is the value? So T11 stands for temperature of the ambient air at 11 kilometers under ISA conditions. We are assuming ISA conditions here because it says at a standard height of 11 kilometers. Okay. So please calculate and just announce the number. No need to now raise a hand because that is too cumbersome. Just speak out. 216.66 degree Kelvin is the temperature. So if that is known to you, how do you get the value of density rho? Because you need half rho V square, so you need density. Does anybody remember how to get density ratio? Yes, what is it? It is T by T naught to the power. I'll help you. Here is the formula. Okay, this is the formula. Now remember, there is a negative sign in the exponent, plus this L is the lapse ratio, which is also minus 0.0065. So actually the exponent is positive. If you take it as, what is R? Universal gas constant, 287 joules per kg degree Kelvin. So R is 287, L is 0.0065, G0 is 9.807. So rho by rho 1 is equal to T by T1 times that ratio. If you take rho as rho 11, then rho 1 will be, so here is the solution. So this is the formula. I have simplified it for you, and this formula I would request you to memorize because you will use it many times. Density ratio up to 11 kilometers. Chances are that when you do aeronautical engineering, you will not go beyond 11 kilometers. When you do aerospace engineering, you will go beyond 11, but for most cases you will be within 11. Within 11 it is very simple, temperature ratio to the power 4.257. So please do it now. T11 is 216.66, TSL is 288.16, find the ratio and multiply by sea level density, which is 1.2256 kg per meter cube. Just speak out the value of density at 11 kilometers if you calculate it. .3648 kg per meter square. Actually meter cube, that's a mistake. I'll correct the mistake. Thank you. Okay, everybody got it? Right. So that is the density. Now here I want to ask you one more small question. Suppose the conditions are not ISA, but let's say ISA plus 20. Once again I am giving you a hint for the quiz. Suppose the temperature is not ISA but ISA plus 20. Then how do you calculate density? Can somebody tell me the procedure?
By adding 20 degrees to the sea level temperature.
Okay. So if I take sea level temperature as 288.16 plus 20 and repeat everything, will it be correct? No, it will not be enough. There is one more thing to be done. Remember, the value of density at sea level 1.2256 is under ISA conditions. So even that you have to change to ISA plus 20. The density of air is a function of temperature also, correct? So now how do you get density of air at temperature T equal to 20? More than ISA. So then now you invoke P is equal to rho RT, okay. R is the same constant. Now here we make an assumption that the pressure is going to be the same. So ISA plus 10 or 20 or 30 doesn't change the pressure, it changes only the temperature. So, assuming P equal to P0, 101,325 Newtons per meter square, rho P is equal to rho RT. So, P is known, R is known, T is known, which is 288 plus 20. Get the new density, it will be 1.6 approximately. Then use 1.6 and 288 plus 20, you will get the density at 11 kilometer under ISA conditions. Yes.
Why can't we directly use ISI conditions?
Because you may be flying this aircraft in the desert in Rajasthan, where we don't have ISA conditions.
But if we say ISI plus 20, we calculate the values at 11 kilometers taking this as a reference. So instead, even if we take ISI as a reference, then we should be getting the same values. Right?
How can you get same values?
Because if it's on the same.
Did you attend the first lecture on atmosphere? So I clarified to you that the forces and the loads acting are a function of temperature. So if the density changes, then the dynamic pressure will be different. So then the whole calculations will be different. So if you are told that operations are happening at a condition of ISA plus 20, you cannot use ISA numbers, you will get wrong values. See, the atmosphere at a place where we are flying is not equal to ISA. In the questions in the classroom textbooks, we assume ISA for ease in calculation. Okay? Alright. How do you get A? Root of gamma RT. So what is the value? How much? 295. Yes, that's correct. So we have now the value of A, that is the speed of sound at 11 km under ISA conditions, 295. Now let's go ahead. How do you calculate now the V? That is simple, 2.2 times this particular value. Okay, so keep going, give me the answers. How much? 649.11 meters per second. That is the speed of the aircraft. So if that is the case, what do you need next? You need the value of half rho V square, dynamic pressure. So rho is the value that you got, 0.3848, V is 649.11. Get the value of dynamic pressure. Now let me warn you, this is one place where many people will make a mistake in the numerical value. So tell me the answer. What is the dynamic pressure? 7685 what? What units? 7685 newtons per meter square. Okay. Does anybody dispute this? Yes? 75.8 kilopascals. So who is right now? That is 75,000 Newton per meter square. So this is called as a calculator mentality. So density, punch the value, velocity, punch the value, equal to something, dynamic pressure, units are in Newton per meter square or units are in kg per meter square because density was in kg per meter cube. You don't balance the units, okay. The correct answer is what she said is right. It will be 76852 Newton per meter square. So what you have done is you divided by G, and to divide by G then you have to put kg per meter cube. So what I want to tell you is if you put the units of density as kg per meter cube and if you put velocity in meters per second, you will get the answer directly in Newton per meter square. Okay, let's go ahead now. How do you get the value of CL? Someone said lift is equal to weight. So weight in kgs divide by, no, then you have to divide it. Be very careful when you use now the calculation, the units should be balanced. So that's why every time you have to check the units. CL is dimensionless. So you have to put W upon QS. Q is known to you, S is 19.5. That's why I multiplied it by 9.81 to get it in newtons. Okay, so that is the value of lift. Notice it's a very small lift coefficient. Why is it so small? High speed flight. So what will be the induced drag? CL square by pi AE. This 0.04 will be squared, so it will be negligible. Okay, induced drag coefficient will be also very small and induced drag also will be small because CL is very small. Okay, so we are assuming that no lift is created by the fuselage etc. The whole lift is produced by this wing, which is a simplistic assumption but very much acceptable. The wings in this case would produce perhaps 95% of the lift. So since we know the value of CL 0.0425, we know the Mach number 2.2, it's very straightforward. You can get the value of alpha by a simple inversion. So get me the value of alpha please.
Sir, 0.0233 radian.
Yes, it's radians, 1.33 degrees. Okay. So it's a very small angle. So obviously when you fly at Mach number 2.2, you cannot expect the aircraft to fly at a very high angle. There will be huge amount of pressure drag or form drag if you fly. So now what is the value of the wave drag coefficient, which was 4 alpha square. So just this into alpha. How much is CD wave, drag coefficient for wave?
0.0109.
Yes, 0.00111. So now you can calculate the drag. This into Q into S. What's the value? So notice here I have not used G again because already it is in Newton per meter square. So therefore the answer I'll get will be in newtons. It's Newton per meter square into dimensionless quantity. What's the value? How much? 1651. Approximately 165 kilograms of drag is acting on the aircraft just because of wave drag. Then you have skin friction, you have form and interference, all other drags. Okay, so this is what the second question was. Now the last question before we start our quiz. Any doubts anybody has so far? Okay, same aircraft. The information given on the top is just for your self-study later on, just to arouse your curiosity if you have regarding the aircraft. This was not a very successful aircraft, it was a failure, actually it was a failure, and there are some reasons for the failure. I can discuss it, in fact we have Moodle to discuss that, so it will be nice if somebody can reactivate the group by telling us why F104 is a failure, what went wrong, what are the problems with it, why such a nice aircraft or such a good looking aircraft did not actually succeed. So our job is to plot lift coefficient versus Mach number. So we have a very thin wing of 3.5% thickness. Let's assume alpha at 5 degree. CL is 2 pi alpha. In incompressible flow for very high speeds. So you just start from Mach number 0.2 and go to 0.2. In fact, it's there for all Mach numbers. Okay. So in steps of 0.2, so you start with 0.2, then 0.4. Now this you can divide if you want. I mean, there are groups in the class, so roughly 10 people in each group. So from 1 to 10, each one can take 0.2, 0.4, 0.6, 0.8, etc. up to 2, and just calculate the value in steps. So let's see, just for confirmation, let us calculate the value for m equal to 0.2. How will it change? Actually the question was not CL versus M but CD versus M. None of you have observed it and none of you has pointed out that question. So just see, CL is already given as 2 pi alpha. So what is there with Mach number? If alpha is 5 degree, then CL is 2 pi alpha. And what happens in compressible? That's right. So you have to start with the value at low Mach number and then apply Prandtl-Claude rule and calculate the value before and after. Okay. So here it is. This is how it will come. And the area between Mach number 0.9 and 1.1 we are not plotting, because that is the area where you cannot use this Prandtl-Claude rule. You can use it up to some transonic value and beyond that value. Okay.